I'm Jeroen van Meij and welcome to my lecture series on computer and network security. In this video on symmetric encryption, I will be talking about block ciphers and one of its most famous examples, namely DES. Well, let's start with the general substitution ideal block cipher. A block cipher operates on plain text blocks of a certain number of bits to produce ciphertext blocks of the same size. For a block size of n bits, there are 2 to the n possible different plaintext blocks. And for the encryption to be reversible, each must produce a unique ciphertext block. Let's take a look at this example with 4 bits of input. Clearly, a 4-bit input block has 16 possible values ranging from 4 times 0 up to 4 times 1, which is 15 in decimal. Each of these is mapped to one unique output block. For example, 0000 is mapped onto 14, which corresponds to 1110. So there's a unique mapping where each possible plaintext block is mapped onto a unique ciphertext block. It has to be unique so that the encryption is reversible. This ideal block cipher has some problems, however. For a small block size, like 4 bits, it becomes equivalent to the traditional substitution ciphers that are vulnerable to frequency and other statistical attacks. For a large block size, it becomes impractical, as the mapping of plain onto ciphertext blocks needs to be captured in the key, and this key grows exponentially with the size of the block. For example, here you see a possible mapping, the same one as on the previous slide, for a block size of 4 bits. The key has to capture this full mapping to allow decryption. As a question to you, I would like to ask what is the required key length in bits to capture the mapping for the ideal block cipher with a block size of n equal to 4. Feel free to pause the video if you want to think about this question. And let's take a look at the answer. The correct answer is 64, number D. Why is it 64 bits? Let's take another closer look at our example with all possible blocks of 4 bits. Each of these is mapped onto a unique ciphertext block, also of 4 bits. We can capture this mapping by putting one by one the associated ciphertext blocks one behind the other, starting with the one that corresponds to 0, then 1, 2, up to 15. By putting them in order, we obtain a unique mapping. Looking at this key, we now know that 1110 is the ciphertext corresponding to block 0. 0100 corresponds to block 1, 1101 to block 2, and so on. In total, this mapping contains 16 different blocks of 4 bits each, so 64 bits. So our key is 64 bits long, which was the answer to the question. We can generalize this to a block size of n bits, and then the key length is n times 2 to the nth power. So it becomes exponential as a function of the length of the block. Feistel came up with a more practical block cipher, where the key size does not grow exponentially with the size of the blocks. Every Feistel cipher follows the same general structure, where the size of a block is 2 times W. The block is then split into 2 equal parts, with first a permutation being performed where the right block becomes the left block, or the right half of the block becomes the left half of the block, and the left half is transformed using substitution and then becomes the right part. How is it transformed? Well, the right half of the block is first transformed and combined with a key using the round function f. This is the round key, which is derived from the main key. And then, using an XOR operation, it is combined with the left part of the block to create a new right part. Feistel cipher therefore combines substitution and permutation. It is characterized by its round function. This process is then repeated multiple times in a row for a certain number of rounds. And I have an exercise that you can do on your own at home. And the exercise question is to calculate the output of Feistel's encryption algorithm with the following input variables. Considering a plain text block of 8 bits, 11010011, a round subkey of 2 bits, 0101. As a round function, we will use bitwise AND, and we will execute a single round. So my question is, given this plain text block and this round key, round function, and one round, what is the associated ciphertext output block, which will also be 8 bits? The most known example of a Feistel cipher is the Data Encryption Standard, or DES. DES was developed in the 1970s by the National Institute of Standards and Technology, or NIST, or was standardized by NIST in 1977. And it was the most used encryption scheme until the introduction of AES, Advanced Encryption Standard, in 2001. At the basis of DES lies DEA, which is the data encryption algorithm. It uses blocks of 64 bits and a key of 56 bits. However, it is right now considered insecure. Triple DES increases the security of DES by executing the DES algorithm 3 times and thus increasing the key size, and this one was introduced in 1999. And I won't go into details of DES as it's not considered secure anymore anyway, but I will give you an overview of the high-level operations. And as I said, DES is a Feistel cipher, so just as a general Feistel cipher, it's executed over multiple rounds, where each of the rounds uses the Feistel structure. Specifically, DES has 16 different rounds, where the 64-bit input is transformed in a 64-bit output. The round function f performs expansion, substitution, permutation, and XOR using the round key. The round key is 48 bits and is derived from the general key K. This key is 64 bits, however, the 8 last bits are ignored. So practically the key is only 56 bits large. From this 56-bit key, we derive 16 48-bit round keys. And the main problem of DES is its use of a 56-bit key. And why does it use such a short key? Well, this can be traced back to documents from the 1970s discussing the design of DES by IBM. And IBM was discussed this with the NSA in the US, and the NSA helped IBM to strengthen the algorithm against all kinds of attacks, as you can read here, except brute force attacks. This was because the NSA wanted to be able to decrypt messages for example, spying purposes. NSA actually pushed IBM to use a 48-bit key. However, ultimately they compromised on a 56-bit key. The problem, of course, is that not only NSA can now decrypt these messages, but also other attackers that may have malicious goals. And in the 1970s, a 56-bit key was still relatively secure. It was very hard to brute force such a key, but as time went on, computational power increased and it became easier and easier to crack DES. So let's say we would brute force this key. There are 2 to the 56 possible keys. If we attempt one decryption per microsecond, it would still take about 1000 years. The problem, however, is that modern hardware is much faster than that. And if we look at regular computers around the year 2009, more than 10 years ago, they would be able to crack DES in about 1 year. A 2012 supercomputer would be able to do this in 1 hour. And modern computers from the 2020s do this in even less time. If we compare this to AES or triple S, they require much more time to be brute forced, and they are thus computationally secure, while DES is not. And actually, successful brute force attacks have been conducted already as early as 1997, before AES was developed. As early as 1977, so in the year DES was first proposed, Diffie and Hellman already proposed a theoretical DES cracking machine. They never built it, but they showed that for about $20 million it would be possible to build such a machine that could crack DES in 1 day. In 1993, a better design was proposed that would cost only $1 million and could find a key in about 7 hours. A few years later, the Dishell project was the first to decrypt an actual DES encrypted message, at least publicly, using a distributed algorithm that used the idle cycles of thousands of computers across the internet. And they actually won a prize for that. And in 1998, the first DES cracker machine was built by the Electronic Frontier Foundation for only $250,000, which could crack a DES key in about 2 days. This therefore shows that at the moment DES is definitely not secure anymore, it's not computationally secure and should not be used. As a quick fix, they proposed so-called triple DES. It's an alternative to DES that reuses the original DES algorithm and thus does not require any changes to the original algorithm and allows you to reuse hardware developed for DES encryption. And uses 2 or 3 different keys to perform 3 encryptions in a row. There is a 2-key variant where the last key basically is replaced by reusing the first key. So the reason that it does encryption, decryption, encryption rather than encryption, encryption, encryption is for backwards compatibility. Because if you do encryption, decryption, encryption, and you set all 3 keys equal to each other, so using only a single key, you will first encrypt the message, decrypt it with the same key, and then encrypt it again. So it becomes equivalent to traditional DES. So that's the reason there is a decryption step here in the middle instead of an encryption step. Then the decryption process is the inverse, so you first do decryption with the 3rd key, encryption with the 2nd key, and decryption again with the 1st key, which results back in our plain text message. And let's summarize what all the different ciphers that we talked about up to this point. So we started in the first lecture with traditional historical ciphers, like the Caesar and the General Caesar cipher. These, however, were vulnerable to brute force attacks due to the extremely small key space. Then they proposed several mono and polyalphabetic substitution ciphers to address the problem of the small key space. However, monoalphabetic cipher and polyalphabetic ciphers like the Vigenère cipher are vulnerable to frequency attacks and therefore should not be used either. The one-time pad was the first unconditionally secure cipher. It's a stream cipher, but it's practically infeasible due to the fact that the key has to be the same size as the plaintext message, which makes it very hard to securely distribute this key. RC4 and Salsa are two other stream ciphers that solve this problem by using a pseudo-random generator to generate a key stream based on a shorter key. However, RC4 introduces bias into this pseudo-random key, which makes it insecure. Salsa 20 is at the moment still considered computationally secure with large enough key sizes, like for example 256 bits. Then we talked about block ciphers, DES, and triple DES. DES is vulnerable to brute force attacks due to the relatively small key size of 56 bits. Triple DES solves this problem by using 3 different keys, thus increasing the key size to 168 bits. However, as triple DES has to run the encryption algorithm 3 times in a row, it is computationally very expensive. As a solution for this problem, they came up with a new block cipher to replace DES, which is called the Advanced Encryption Standard. And this Advanced Encryption Standard, or AES, will be the topic of the next video.